Hello everyone, myself Gargi Roy. I am the Assistant Professor of Electrical Engineering Department of JS College of Engineering. Today I am going to discuss about the illumination engineering subject, which is generally taught in the 7th semester of BTech final year, and also it is taught in diploma 5th semester. Now I am going to discuss the course objective of this subject. To provide an introduction to the fundamentals of illumination engineering and architectural lighting design, and also to impart lighting fundamentals, measurement, and technology and their application in the analysis and design of architectural lighting system. Next, this course has some outcomes by which students will be able to understand the need of good illumination and learning the physics behind various luminous sources, other terms and units. And also they will be able to identify the criteria for the selection of lamps and lighting systems for an indoor and outdoor space. They will be able to perform calculations on photometric performance of light sources and luminaires for lighting designs and evaluate different types of lighting designs and applications. Now, course overview. Course overview is color temperature, and another course overview is characteristics of light. So first of all, I want to say that basically illumination, that means it is based on light of physics. So this illumination engineering is based on the light sources. Our natural light source is sun, which is the main light source, but nowadays different types of artificial sources are present in our life, without which we cannot do anything, because for a particular time we can get sunlight from the sun. So some physical processes employed in the artificial sources. This topic will be discussed now. So first one is incandescence. Thermoluminescence is by definition radiation at high temperature. The sources employing this process are incandescent lamp, gas lamp, like flames, and in oil lamps and wax candles. They lead to a continuous spectrum of radiation. Next, luminescence. Luminescence, electroluminescence, by definition, chemical or electrical action on gases or vapor radiation. Here, color of radiation depends on the materials employed. Usually, this process leads to line or band spectrum. Next, fluorescence. Fluorescence is a process in which radiation is absorbed at one wavelength and radiated at another wavelength. That is UV impinging on uranium. Fluorescent oils. This re-radiation makes the light radiated visible. Next, phosphorescence. Phosphorescence is a process when energy is absorbed at some time and radiated later as glow. Examples of this process are luminous paints that contain calcium sulfide that lead to phosphorescence. They produce light radiation after exposure of light. Okay. Next, another important term is color temperature. I think all of you know about the color, but it is a characteristics by which we can recognize any object. So generally, there are three types of primary colors: red, yellow, RGB, that means red, green, and blue. Now, color temperature. The color temperature of a light source is the temperature of an ideal black body radiator that radiates light of a color comparable to that of the light source. Color temperature is a characteristics of visible light that has important applications in lighting, photography, videography, manufacturing, horticulture, etc. Okay. Now, Now, color temperatures over 5000 Kelvin are called cool colors, that is look like bluish, while lower color temperature, that means 2700 to 3000 Kelvin, are called warm colors, that is yellowish. Warm in this context is an analogy to radiated heat flux of traditional incandescent lighting rather than temperature. So in the right side you can see a picture where different color temperature are present for different types of lamps. So in the left side 2700 Kelvin where 60 watt incandescent lamp is present. Next in the right side 3500 Kelvin 3500 Kelvin for 13 watt fluorescent lamp and another 5500 Kelvin for 13 watt fluorescent lamp. So different types of lamps are present here. Next, for color temperature, for radiation temperature of the materials, we follow Stefan-Boltzmann law. So according to the Stefan-Boltzmann law, the total radiant heat power emitted from a surface is proportional to the fourth power of its absolute temperature, where the equation will be W equal to K into T to the power 4, where K tends to 5.67 into 10 to the power minus 8 watt per meter squared per Kelvin to the 4th. It's called as Boltzmann constant or radiation constant, and where T equal to absolute temperature. And from this we can get W equal to K into T to the power 4 minus T0 to the power 4 watts per centimeter square. So where T0, that means T suffix 0 is called as ambient temperature. Thus energy radiated depends on the fourth power of temperature. So efficiency is high at high temperatures. The law applies only to black bodies, theoretical surfaces that absorb all incident heat radiation. So in the lower portion you can see that the same place is observed in different way, because in the first picture it is seen as warm white, and next cool white, and the last one daylight. So in warm white situation, how the object and the place looks like, and at cool white situation how the place looks like. Similarly at daylight how the place looks like. So these differences are formed because of color temperature. Next, black body radiator. What is black body radiator? A black body radiator is any object which fully absorbs all frequencies of light, just as white body in any object which fully reflects all frequencies of light. It is very known to us that white body is any object, it fully reflects all frequencies of light. But a black body, it fully absorbs all frequencies of light. Now, black body radiation is the type of electromagnetic radiation that is emitted by a black body, which is held at constant and uniform temperature. That radiation has a specific spectrum and intensity that depends only on the temperature of the body. In another word, the hue or color of specific spectrum of light emitted by a black body radiator is determined by its temperature. The sun or tungsten incandescent filament lamp are both examples of near perfect blackbody radiators. And the temperature of the blackbody radiator is measured in degrees Kelvin, and therefore the color of light emitted by a blackbody radiator can be determined by its temperature in degree Kelvins. So in the right side we can see a graph, intensity versus wavelength, where you can see that for infrared and ultraviolet, that has a particular wavelength and bodies radiating at similar temperatures, like surface of the sun, that is 6000 Kelvin. Carbon arc lamp has color temperature of 4000 Kelvin, and filament lamp that has 3000 Kelvin color temperature. Next, characteristics of light. All of you know that light is a radiant energy. When light enters in a prism, it is divided into 7 colors. That is called as VIBGYOR. So, light has some characteristics. It has a particular velocity, that is 3 into 10 to the power 8 meter per second. When light encounters a surface, it can be reflected away or the refraction will be happening. So once in the material, the light can be transmitted, absorbed or diffused by the material. So first, incidence. What is incidence? The striking of a ray of light or sound on a surface. Next, another characteristics of light is reflection. That is the return of light, sound or radiant heat after striking a surface. Next, refraction. The process by which the direction of light changes as it passes from one medium to another, in which its speed is different. Next, reflection. There are the 3 general types of reflection. First one is specular, next spread, and after that diffuse. So specular reflection occurs when light is reflected away from the surface at the same angle as the incoming light's angle. Next, spread reflection. It occurs when an uneven surface reflects light at more than one angle, but the reflected angles are all more or less the same as the incident angle. So in the right side, number A picture has polished surface, and when light is reflected from the surface at the same angle as the incoming light's angle. So it is the picture of specular reflection. Next, picture number B, where surface area is rough. So for this uneven surface, light reflects at more than one angle, and reflected angles are all more or less same as the incident angle. So this is the picture of spread reflection. And last one, diffuse reflection. It's sometimes called Lambertian scattering or diffusion. Occurs when a rough or matte surface reflects the light at many different angles. So the third picture says about the diffuse reflection, because here the light scatters in different angles. Now, law of reflection. So specular reflections demonstrate the law of reflection, which states that the angle between the incident ray and a line that is normal to the surface is equal to the angle between an incident ray and the normal. The angle between an incident ray and the normal is called the incident angle, and it is denoted by the symbol theta. So here we can see that this is the surface. From the source, light enters in the surface, and after that it is reflected. Okay. So the angle between the incident ray that is theta is equal to the surface is equal to the angle between the incident ray and the normal. The angle between an incident ray and the normal is called the incident angle. So this is called as incident angle. It is denoted as theta. And the angle between a reflected ray and the normal is called the reflected angle, that is denoted as theta dash. Okay, next, refraction. When light travels from one material to another, such as from air to glass, it refracts, bends, and changes velocity. Refraction depends on two factors, the incident angle and refractive index of the material, which is denoted as N. The index of refraction for a particular material is the ratio of the speed of light in a vacuum to the speed of light in that material. Now N equal to speed of light in vacuum by speed of light in the material, that is equal to C by V. So the speed of light in air is almost identical to the speed of light in a vacuum. So the incidence index of refraction for air is considered to be 1. The index of refraction for almost all other substances is greater than 1 because the speed of light is lower as it passes through them. So it is very important law for refraction, that is called as Snell's law. Snell's law of refraction shows the relationship between the incident angle and the refractive index, where n1 sine theta 1 equal to n2 sine theta 2, where n1 equal to the refractive index of medium 1 and n2 equal to the refractive index of medium 2. So in the right side picture, first air medium is present and in the lower portion is glass medium. So here theta 1, that is the incident angle of the light ray with respect to the normal, and theta 1 dash the reflected angle with respect to the normal. But where theta 2 is the refracted angle, because here this incident ray is refracted due to the change of the medium, because incident ray is in air medium but refracted ray is in glass medium. So N1 and N2 both are not same because the mediums are changed, because N1 equal to refractive index of medium 1 and N2 equal to refractive index of medium 2. Okay. Next, transmission. So when light passes through an object, it is called transmission. So suppose this is an object and this is a light source, and from this light passes through, so it is called transmission. Absorption, reflection, refraction, and diffusion all affect light transmission. Next, absorption. Instead of completely transmitting light, an object can absorb part or all of the incident light, usually by converting it into heat. Okay. Many materials absorb some wavelengths while transmitting others, which is called selective absorption. Now, Lambert's law of absorption states that equal thickness of a given homogeneous material absorb the same fraction of light. In other words, if a 1 centimeter block of material absorbs half of the incoming light, just like this picture, 1 centimeter blocks is present here. If it absorbs half of the incoming light, a second 1 centimeter block of the same material would again absorb half of the beam, so that only 0.5 into 0.5, that means 1 by 4, that means 1 by 2 into 1 by 2, that is equal to 1 by 4, or 0.5 into 0.5 or equal to 0.25 of the original light is transmitted through a total of 2 centimeter material, because this is 1 centimeter and here is 1 centimeter. So 1 plus 1 equal to 2 centimeter. So 2 centimeter blocks absorbs 1/4, that means 0.25 of the original light. This is called Lambert's law of absorption. And last characteristics is diffusion. When light strikes a rough surface, the light is reflected or transmitted in many different directions at once, which is called diffusion or scattering. The amount of diffuse transmission or reflection that occurs when light moves through one material to strike another material depends on two factors. Number one, the difference in refractive index between the two materials, and another one, the size and shape of the particles in the diffusing material compared to the wavelength of the light. So, for example, the molecules in here happen to be the right size to scatter light with shorter wavelengths, and the result is we get blue sky. So this is the picture of diffuse transmission and diffuse reflectance. Okay. So these are the today's topics, and the references are, some books names are present here and some web links are present here. Okay. Thank you for your kind cooperation.